Hello, everybody. This is one of the videos to accompany our course. It's basically covering section 5.2 of the textbook on confidence intervals for a population proportion, and it goes along with the section 5.1 and 2 DA that we're working on. So you should be at your computer and logged into RStudio, and you should stop the video from time to time to run the code that is suggested and see what effect it has. All right, let's get going. Confidence intervals. So if you're one of the very few people who does frequently restart R, then make sure that you run library tigerstats, because that's the package that you will need today. So, how to make a confidence interval for a single population proportion P. So just to remind ourselves and catch up, when you're interested in knowing about a population proportion P, then you look at your sample proportion P hat. And P hat is just X, the number of people who said yes to your yes-no question in the sample, divided by N, the number of people in the sample total. That proportion is your single best guess at the population proportion P that you don't know. It's probably off from P by some amount. So a natural question is, could we provide a range of values for P that should be considered as plausible possible values for P based on that data that we have? And the concept of standard error can help us to do this. So recall that the standard error of a point estimate is a measure of how much it's liable to differ from the parameter. So we always say to ourselves, the parameter that we want to know is about equal to our point estimate that we got from our data, give or take a standard error or so. And you would be surprised to learn is if the parameter turned out to be more than 2 standard errors away from the point estimate. So an idea for getting a range of plausible values for P is to use P hat, the sample proportion, and the standard error for P hat together. So we're going to use them together to create what we call a 95% confidence interval for P. The 95% confidence interval for P is a range of real numbers that lie between the following 2 real numbers. This real number, called the lower bound, and this real number, called the upper bound of the confidence interval. So the lower bound is the sample proportion P hat minus 1.96 times the standard error. That's that square root expression there, the standard error for P hat. Whereas the upper bound is P hat plus 1.96 times the standard error for P hat. And so you naturally have some questions. First of all, why would we call this a 95% confidence interval? What's with the 95% confidence? And what's that number 1.96 doing there in the formula? So we're going to find these things out, but first let's just work an example to see if we can compute these things. So suppose you wanted to estimate the proportion P of all Georgetown College students who are female. You know, that's 1,000 students, and maybe you don't have access to all of them to ask them whether they're female or not. And so you take a sample. So in Math 111 survey, we have that sample of 71 students, and they told us their sex. So maybe we could calculate the proportion of people in that sample who are female. The prop command does that if you just say that you want to work with the proportions of sex out of the Math 111 survey data frame. And since female comes before male in the alphabet, it'll compute the proportion of females in the sample. Out of the 71 people in the sample, the proportion that were female was about 0.56, about 56.3%. That's our p hat. Okay, next up, we want to compute the standard error for p hat. Now that was that square root stuff. So we use our calculator and we say squirt for square root of, that's the parentheses, p hat times 1 minus p hat, and then we divide by n, the sample size. So following the formula, we now have the standard error. I have bound the name standard error to the result of that, so you could, if you wish, just sort of print it out and see it. And it turns out to be about 0.0588. So our best guess is that about 56.3% of the population is female, but our guess could be easily off by 5.8% or so. Now we stick them together to make a 95% confidence interval for P. We will do our P hat, that was the 0.56, minus 1.96 times the standard error, and we get our lower bound, 0.448. And P hat plus 1.96 times standard error gives us the upper bound, about 0.678. In percentage terms, the 95% confidence interval is 44.8% up to 67.9%. The point estimate of 56.3% sits right in the middle of that range of real numbers. So there we are. We think that the plausible range of real numbers that we think that the plausible range for what the population proportion really could be is somewhere between 44.8% and 67.9%. But it still remains to be seen where does the 1.96 come from and why are we 95% confident? First of all, let's tackle that 1.96 question. I'm not going to give you the full mathematical argument for the use of that number, but you can actually see that it has something to do with the standard normal distribution. That's the normal curve where the mean is 0 and the standard deviation is 1. If we were to ask for a graph of that curve and look for the chance to fall within minus 1.96 to 1.96, then we would get this graph that you see here. And as you can tell, the area under the standard normal curve between minus 1.96 and 1.96, that shaded blue area here, is just about 95%, 0.95 to several decimal places. So the 1.96 connects us to this 95% confidence that we say we have in that interval. Now, what if you wanted to be more confident that the unknown population proportion P lay in your interval? You would need to make your interval wider, cover a wider range of possible values for P. But how wide should you make it? It turns out that you work the same way, but your lower bound is going to be got by doing 2.58 times the standard error for P hat. And the upper bound will use the 2.58 number as well. Just as an example, say that you wanted to use that same data to compute a 99% confidence interval for the proportion of all Georgetown College students who are female. All you have to do is take your population proportion, that 0.56, and do minus 0.258 times the standard error that you found. And similarly, plus 0.258. And so turning these lower bound proportion and upper bound proportion into percentages, we get that their 99% confidence interval runs from 41.2% to 71.5%. So that's a wider range than before, but we're 99% confident that P lies within that range. With the narrower interval, we were only 95% confident. Again, why the number 2.58? Well, if you ask p-norm GC to tell you the area under the standard normal curve between minus 2.58 and 2.58, then you see that that area is just about 0.99. So you can see that the 2.58 has been carefully selected to go along with this notion of 99% confidence. Still want to talk to you about why we feel these different levels of confidence, 95% confidence interval, 99% confidence interval. And we'll get to that. But a way to get to that is to dive into talking about how you would interpret confidence intervals to other people once you've computed them. How do you explain what they mean and what they tell you? So back to our 95% confidence interval for the proportion of all GC students who are female, went from the 0.44 to the 0.67. How would we interpret this? How would we explain it to other people? Well, one really simple way is just to say to them, we're 95% confident that the percentage of all Georgetown College students who are female is between 44.8 and 67.9%. I left out who are female in this sentence, and I will fix that in the slides. Here's another good way to explain the confidence interval to people. If they ask you, well, why are you 95% confident? You could say that you happen to know that if a lot of statisticians each came along and took their own samples from the population and computed their own confidence intervals using that same formula that we did, then about 95% of them would get an interval that contains the real population proportion P. Now you might wonder, why is this so? I can illustrate why it's so rather than giving the full mathematical arguments by having you work with some simulations. So let's just suppose for a minute now that you are really like God and you know everything about this population and you know the population proportion. In fact, let's just go ahead and say we know that the population proportion is 0.5. And let's suppose also that we plan to watch a lot of statisticians each take a random sample of size 100 from the population. And we watch each one of them compute a 95% confidence interval using the formula. So given that what each statistician gets in his or her sample is a matter of chance, each of them is going to get different confidence intervals. And some of those confidence intervals will contain the real P, the 0.5, inside of them, and some of them won't. But I'm interested in how many of them will and how many of them won't. So we happen to have a little function available in TigerStats that allows us to play God and watch these statisticians do their work. It's called watch statisticians slow. This first parameter n says, what's the sample size that these statisticians are going to work with? We're going to set it to 100. They're going to take samples of size 100. The p parameter says, what's the real value of the population proportion? We'll set it to 0.5. How many statisticians do we want to watch? We can set that in 1, 2. That's going to be set to 50 using this interval number parameter. What kind of confidence intervals are they going to make? Let's make them do 95% confidence intervals. The level parameter specifies what confidence interval they're going to make. So we're going to try this out. And I'm going to go ahead and try it out, and you can just try it out as well after you watch me do it. So I'll take this command, copy, and I'll head to RStudio, and I'll paste it into the console. And I get some stuff going on here, and I need to get myself out of the way. I'll do that. Okay. And I think I will also widen up the graph a bit, make it a bit bigger for you to see. Alrighty. And you can see down in the console that it's asking, take another sample. So, gee, have we taken a sample already? Oh, yes, we have. Looking back at the graph, what we see here is on the x-axis, the real numbers from 0 to 1, like all possible proportions, from 0% to 100%. And we have a blue dotted line at the real population proportion of 0.5. And there's this kind of grayish interval here. That is the first confidence interval the first statistician made based on his or her sample of size 100. The dot in the middle of the interval is the sample proportion that this statistician got. The interval contains 0.5 in it. So the statistician will never know this, but they got a quote-unquote good interval. It contained the real p. Okay, let's go back to the console and let's indeed take another sample. So here comes another statistician, ready, set, go. That second statistician got a sample proportion a little over 50%, and her interval also contained p. Let's go again. And again. Each time, these statisticians are sampling 100 people out of the population and making a 95% confidence interval. Because their samples are all different, their intervals are all different. But so far, all those intervals have contained the real population proportion. Let's keep going. I've made quite a few intervals so far. All of them have contained p. Oh, whoa, let me back up there. It looks like one of my statisticians got kind of an unlucky sample. The sample proportion for that statistician was way under the 0.5 that the real p is. So even after the statistician made the lower and upper bounds for the confidence interval, the upper bound for the confidence interval was unable to make the whole interval contain 0.5. This statistician will never know it. She'll end up believing that probably the real p is somewhere rather small down here and miss out on the actual value of p. Okay, let's keep going. Oh, there's another unlucky statistician. Remember, we've set it for 50 statisticians to do their work. Looks like we're getting pretty close to the end. Yep, now we're all done, says the console. 50 statisticians have done their work. 3 out of the 50 have had bad intervals. Now, 3 out of 50 is the same ratio as 6 out of 100. That's 6%. So 94% of these statisticians got good intervals. They got intervals that actually contain the real population proportion. Let's head back to the slides. If you want to see this happen all at once, then you can run a function called watch statisticians. And it just goes ahead and does it all for you. You don't have to ask for the statisticians one at a time. And so if you were to try to run this in your console, and I recommend doing it, you'll get different results from me because it's all based on random data. But most likely, a couple of times out of 50, you'll get unlucky statisticians. On average, what's happening is that 95% of the time, the statisticians get intervals that contain the real population parameter. That's an absolute math fact. So we're not going into the demonstration mathematically, but I hope that this simulation has made it plausible to you that there really is this connection between the 1.96 and the 95% area under the standard normal curve and being 95% confident, having that 95% chance that your interval is going to contain the real population proportion. Just keep in mind that in real life, you're not God. You don't get to watch a bunch of statisticians do stuff. You're the statistician, and you're probably only going to get to take one sample. But because there was a 95% chance before you took the sample that that interval would contain P, you can feel 95% confident that your interval is an interval that contains P. So we've seen a couple of really good ways to interpret confidence intervals to other folks and to ourselves. Let me look at a couple of bad ways to interpret confidence intervals. These are interpretations that people, quite often trained professionals, are tempted to give, but we do need to avoid them. One bad interpretation is we're 95% confident that, oh dear, and this is an outdated slide. So I'm sorry, I'm just going to have to skip over it. It needs to be about proportions and not means. And oh dear, again, another one. So I'll tell you what I'm going to do. I'm going to end this video presentation, fix up these slides, and then do another video that continues the presentation from slide 28 corrected. Bye-bye for now.